What if the most valuable skill an engineer can master isn't aerodynamics or code, but the ability to learn faster, build better, and pass knowledge forward so the next generation can outpace us? Welcome to Industry Ignited, the podcast where we explore the leaders, decisions, and innovations shaping the future of industry. I'm your host, Dr. Leeanne Aguilar, and today I'm joined by Dr. Rashid Ali, Senior Lecturer at Coventry University, an aerospace educator, UAV designer, flight simulation innovator, embedded systems expert, and a true believer in one powerful mindset. Impossible merely states, I'm possible. Dr. Ali, welcome to the show.
Good afternoon or good morning to you as it happens in the Central. Thank you very much for having me on your podcast. Looking forward to a meaningful and fruitful conversation.
Great. Thank you so much for joining me. Now, you've said you were enchanted by flight from childhood and even earned a pilot license early on. What was the moment you knew aerospace wasn't just an interest, but your life's work?
Yes, a very interesting question. I mean, I can remember as a child stretching my arms wide and running around pretending to be an aeroplane, looking towards the sky and seeing how do these birds actually fly? So I was fascinated from practically day one. Now, as it may sound, it's not as the romanticism of flight wasn't the one that actually allowed me to pursue aviation as a career and a passion, but it was actually the technical aspects which basically veered me towards aerospace. Now, I started making paper aeroplanes when I was very young, maybe 5 or 6 years of age. I was making and flying paper aeroplanes. And then as the passion got stronger and stronger and stronger, my father decided that he is going to buy me a model aeroplane. Basically, in those days, we didn't have a radio control aeroplane. So we basically had a wireline aircraft propeller with an internal combustion engine and a couple of wires going, strings basically, string line or wire line aeroplane, going to the aeroplane that could only control the aircraft in pitch. So you stood at a distance away and the aircraft would basically go up and down in a circle. And you basically moved around with the aeroplane. And when the fuel finished, the aircraft would then land.
Right. Oh, so interesting.
Then that naturally led me to take up power flying and gliding. Um, but the first time I actually realized that aircraft only work and they work well only if the assumptions of flight survive the reality. For example, if we assume that the aircraft is in perfect balance, well, unless and until it is in perfect balance, it's not going to fly very well. So that assumption has to survive the reality. The control surfaces have to be correct, the mass balance of the aircraft has to be correct, and everything has to work correctly. Now, as a result, I'd often wondered while I was making these model aeroplanes that if I was to make an airplane that was carrying people, and if that aeroplane was to crash because of my ineptness or my lack of knowledge, then there are going to be some serious, serious consequences. So really, the realization that mistakes have consequences led me to think, maybe this is not just a passion anymore. It really needs to be a responsibility. And this responsibility really needs to be for life.
Oh, wow. Okay, that's interesting. So, I find it fascinating too that you're interested in the technical aspects of flight, what was behind it and how it really works, like getting into the functionality and the engineering. So you really had an engineering mind, I'm hearing
That's
from the
right,
start.
absolutely.
Yeah.
And as an aviator and also as an engineer, I was always fascinated by how things work. So I was pretty much hands-on, but obviously everything has a consequence. So it wasn't just anymore an interest, it was actually a passion translating to responsibility and owning up to those responsibility. And that's the sort of mindset I actually grew up with. So that's where we are.
Yeah. No, I think that's fascinating as well, right? Just seeing it as a responsibility to learn how to do it well, how to do it right, and then you not only that, took it into teaching, and so that responsibility carried on to showing others and teaching others. Yeah. S-
Absolutely.
So your career spans aeronautical engineering, flight control research, software development for major industries, and teaching. What were the pivotal turning points that shaped your identity as a polymath engineer educator?
Right, interesting. When I finished school, I wanted to be an aeronautical engineer. I couldn't progress my private pilot license to commercial flying because my mother was scared that I'd die by crashing the aeroplanes. She was dead against me flying. So the next best thing that I could do was to become an engineer so I could still carry on working within the sector. So a friend of my father and my father were discussing my career options when I was only an 18-year-old. So my father said, son, engineering requires a lot of mathematics. So we suggest that you'll become a better engineer if you do a degree in mathematics first.
Ah,
So I actually ended up doing a degree in mathematics first and
uh-huh.
then did a degree in aeronautical engineering. Now, of course, what that meant was I actually started to see from just the equations pictures. So equations meant pictures to me,
Mm,
not just mathematical representation of a physical phenomenon. I could actually see through those equations the physics, the physical things which these equations were trying to describe. And of course, once I graduated, aeronautical engineering then actually became very easy for me because of the very strong mathematical background. Then I
right.
wanted to sort of explore things in even greater depth. So I started a program for a PhD. And whilst during the undergraduate degrees, we were taught about aerodynamics, thermodynamics, structures, computer-aided design, etc. So lots of different areas. What I realized was that aerospace problems don't respect disciplinary boundaries. They have no set boundaries. For example, when I started doing my work on flight control, I soon realized that flight control means I have to understand mathematics, which I obviously did. Then it sort of, veers into flight mechanics, then into electromechanical systems, mechanical systems, electronics, software. So everything becomes an amalgam of things to solve the problem. Now, every time I hit a limitation in terms of knowledge, I basically went and learned the thing that was missing rather than outsource my thinking. So, and that is basically what led me to become a polymathic. Now, also, a very interesting aspect that I discovered earlier on, I mean, I love food and I love cooking, was that every discipline that you have in life teaches you something. There is something to learn, and these are transferable skills which we can translate across our working domain. Now, for example, cooking taught me that timing is absolutely important. If you add the spice at the wrong time, it changes the flavor completely. Not only that, the quantity of spice that you add affects the quality of the food and, of course, the looks. It can change the looks as well. So,
Right.
same thing can be then translated to engineering as well. The timing of information is absolutely the key. If you're not ready to receive the information, if it arrives too early, it has no meaning. If the information arrives after when you need it, it has no meaning. So, from an engineering perspective, this information has timing, just like what when we add spices to the food where we're preparing. Timing is the key.
Yeah, no, that's great insight, and it makes a lot of sense. I remember even in college, for some reason, they let me take organic chemistry before I took basic chemistry, and so somehow I managed to get, I think, a B in the class, but it was like completely did not make sense. I did not get it. And then when I went back and finally took chemistry, it all made sense. And I'm like, oh, well,
That's
duh,
how it
you know?
works.
It's like I
Yeah,
didn't have that foundational knowledge. And so once I had it, yeah, it's like that sequence is important in having
absolutely.
information, and there's a reason why they should give you, you know, courses in a certain order so you're ready to
Well, also, Leanne, I think it's fair to say that knowledge is incremental. We build just like, well, we have a foundation, then we have the ground floor, then we have the first floor of a building. Knowledge exactly the same thing. We have to build upon our past experiences. We then sort of look upward to see where we can potentially go, and then that's how we chart our progress.
Yeah, that's true. Now, your mantra, knowledge taken to the grave is useless, is a strong stance. Where did that belief come from, and how
Oh,
has it shaped you the way that you lead and teach?
yes, I mean, I've often said that knowledge taken to the grave is useless. I mean, we have to leave the knowledge here on this planet for other people to actually get benefit from. Now, I can go back in history, and I've had many wonderful mentors who have selflessly passed on what they knew and shaped me who I am today. So I am eternally thankful to those people. And yet, I did come across one or two people who were brilliant in what they did, but they were very cagey about divulging the full extent of what they knew. They were always reserved. They were always trying to guard, as it were, what they knew. And so they would never come out and give you everything. Now, as a
Hmm.
result, I discovered that, maybe it's not such a good idea to hoard knowledge. So if you hoard knowledge, it actually slows progress. Whereas if you impart that knowledge freely, it actually multiplies it because you've transferred the knowledge. Now, the way I think it works, now I might be slightly wrong, but I believe that if I showed somebody multiple ways of doing it and then left that person to choose his or her direction, then what I've done is I have created a framework where there is a time reduction. So they don't actually have to go and find out the different ways of doing something. So they have been told these end ways, but they still make up their own mind, which then means that somehow they've now got some extra time available. Now, in that extra time, they can actually make that progress. So from
Right.
that point of view, I've always thought of engineering as being able to enable others, right? So if I
Yeah.
can enable others to do things what I do more efficiently, then I think I'm on a winner.
Yeah.
And I've always said to my students, nothing pleases me more than to see you become a better version of me.
Yes. No, that's great. And I think it is interesting when people hold on to information. I think they're afraid to give the secret sauce because they're losing some kind of power or something. I'm not really sure why people do that, but I think as academics too, that is our mission. That's what we're entrusted in with, is building on knowledge, and we depend on the knowledge of those who came before us. And that transparency is important. That, those building blocks and the secret sauce is important, because without it, we're reinventing the wheel all the
Yeah,
time.
we're
And
wasting
that, like you
time
said, we're
almost. We're
wasting
wasting
time.
time. We're
Yeah.
wasting
Yeah.
time because, we are having to do everything that our forefathers did, only to find out what they did. Now, if they basically
Exactly.
pass that on to us, then obviously then we don't have to go back and, as you rightly say, reinvent the wheel. We basically go from the fourth step rather than having to climb the first, second, and third steps. So
Yes.
that's also very, very important.
Yeah, absolutely. And so if we look beyond ourselves and look for future generations, then equipping them with all that we know is, like you said before, a responsibility, and something that yeah, it's
And we
mhm.
own up to our actions. We own up to our actions, and we make sure that the information that we disseminate is appropriate, and it actually adds to the enablement. So, I mean, for example, if I start giving erroneous information or contradictory information or sending out wrong signals, then the recipient of that information is confused. So there has to be that clarity in dissemination of information so that it is actually an enabler, and to enable somebody to then see something with clarity and determine their direction. I think there can be nothing better than that.
Now, you emphasize that progress is incremental and built on self belief. Looking back, what experience most strengthened your confidence to keep evolving, even after setbacks or fear, including flying again after an incident?
Yes, that's an interesting one. Confidence, in my opinion, doesn't come necessarily 100% from success. It also comes from failure, because what happens is when we fail, it makes us introspect. And when we start to introspect, we start to iron out the weaknesses that may have been responsible for our failure. And when we have ironed those weaknesses out, it can add to your strengths. So those weaknesses actually then become your strengths because A, you don't fear them, and B, you have ironed them out. So success is important too, but failure, I reckon, is perhaps the better teacher.
Yeah.
Now, I've had a small incident in my life where I was piloting a glider and it crashed. Fortunately and luckily for me, I was able to walk away, albeit badly bruised and injured. So that event in my life actually made me think. It made me evaluate the brutality of the situation with honesty. So basically told me either I quit aviation because it's dangerous, or you rebuild the faith and trust in aviation step by step. And that's exactly what I did. I basically went back to basics and I started to build the trust within myself and my confidence and in the aviation and the aircraft step by step, gradually over time. So what that experience actually taught me was that progress isn't bravery. You could be as brave as you want. I mean, that's not going to necessarily lead to progress. Progress is all about controlled exposure. It's an iteration, and the self-belief comes from evidence. The more you practice, the more feedback that you get, more confident you become in your approach, in your thinking, and in the outcomes. So, yes, all I would say is failures. I've had a few, and every failure has made me a stronger person.
Yeah. Well, and like you said before, I mean, with the failure being a greater teacher, it's because it gives you motivation to succeed. I think it's a motivator as well. And
Absolutely.
you've experienced, it gives you that experience of knowing what it's like to fail. And so that experience in itself teaches you and gives you, yeah, more reason to push forward and to win
Yeah,
and figure things
the
out.
only thing,
Yeah.
Leanne, I would say is it was a very stressful experience. Really speaking, if you can sort of, create an experience in a safe and a controlled environment where no harm can be done, I
Sure.
mean, that would be ideal. But that environment was very unforgiving. I mean, I thank my lucky stars that I actually walked away alive. But that experience certainly did leave a very, very indelible, long-lasting mark on my life. And I did learn to treat everything with great respect.
Yeah, no, that makes sense. Well, yeah, because it's traumatic, it's trauma.
Oh,
So,
total trauma, absolute trauma.
yeah, I totally totally hear you. Um, Now you've led the creation and test flight of 80 plus UAV designs across multiple configurations. What patterns have you learned about what makes a UAV design succeed in the real world versus on paper?
Oh, yes, a very, very interesting a subject very, very close to my heart. Uh, I'm going to say um, the last thing first, and then I'm going to basically say things that's going to justify what I'm just going to say. Tell each and every person who comes into my life that you have to start to understand the problem. A solution is a byproduct of understanding. Okay, so that's the ultimate statement. Solution is a byproduct of understanding. So when it comes to UAV design, number one, very few people have a breadth of knowledge to undertake every aspect of UAV design. So we normally have a design team of people. So the first port of call, or first thing that is necessary for a successful design is a harmonious team that can communicate with each other at the appropriate level of technical competence. Now, that's very, very important. Being able to express any doubt that you have, whether it's in the statement somebody's made or in a technical argument that somebody's put forward or whatever. So being able to communicate effectively is the first requirement for a successful design. That's number one. Number two, we have to understand the constraints, the design constraints. Why are we doing this design? How is it going to be operated? What are the functional requirements, etc. So we have to understand the constraints. We have not designed anything yet. We're just going to understand what our solution may look like and what would be the constraints. Then we start to look at the engineering trade-offs. So what engineering trade-offs do we have which are going to enable a successful design? Bearing in mind that every design that we have, whether it is a small UAV or a large UAV, will have to live within a system, an ecological system, a financial system, a social system, a legal system. So this then becomes a design exercise of systems engineering, that you're designing a system that's
Mhm.
going to coexist with other systems. And these are complex systems in their own right. So the real success in engineering comes from humility, in trying to understand your limitation, in trying to understand the problem, in trying to understand the engineering trade-offs. Now, in terms of design space, I always say that aircraft design is a science and an art. And the design space is incredibly huge. If you ask most design teams to come up with a solution given the same constraints and the same limitations, it's not surprising. They all actually come up with different designs doing exactly the same thing. So that's why I always say that if you understand the problem properly, understand the constraints, understand the engineering limitations, then the solution is a byproduct of your understanding. The solution just basically looks at your face.
Yeah. Well, and I like that. I mean, communication also is like one of the key pillars of the process that you mentioned even first. So it comes, I mean, if you're working with a team particularly, I mean, communication is vital. Without it, you're not going to be successful. And then from there, you're looking at the constraints. You know, what are your parameters that you're working within? What's holding you back? And then from there, going into the design. Now, your teaching model has students design, manufacture, and then fly a UAV. And then they reconcile outcomes against predictions. Why is that close the loop process so critical to producing competent engineers?
Right. I always love going back to the basics. Now imagine you were tasked to warm up something, let's say boil water. And the task was that you're going to keep the water at 80 degrees Celsius. No big deal. So what you do is you take a pot, you put some water, and you put it over the stove and start to heat it. But then when do you know, or how do you know the water has got to 80 degrees Celsius? Well, you need to measure it.
Hmm.
So think about learning exactly in the same way. So the desired output is a skill, let's say, which is what we call a learning outcome, right? Then what are the students learning? We need to assess them, which is where have they got to in terms of their knowledge, in terms of their learning. So we have to do an assessment. So when we compare the learning outcomes with what the students are achieving through an assessment, the error, the difference between what we expect and what the students are demonstrating can then be worked upon. So
Right.
this is closing the loop. So when we come to why is closing the loop important in aircraft design or UAV design or the way I teach is very simple. We design something, we make it, we test flight. So that then closes the loop. So when we test fly the aircraft, we can measure its expected performance to the performance the aircraft is achieving. And then if there are any discrepancies between what we think it ought to be doing and what it is doing, then we have the opportunity to correct what might be the source of the discrepancy. So if you were to just design the aeroplane, which means we are predicting the behavior through analysis only, they can teach you confidence. The confidence would be in the tools that you're using to design, but it doesn't teach you judgment.
Right.
So when we do practice, the practice allows the judgment, and judgment is absolutely important. Why?
Right.
Because when we test something, we have to measure. The measurement generally happens to be these days digital. It's numbers. So, for example, a force of 100 newtons, what does it actually mean? It's roughly 10 kilograms. So we start to get the feel for numbers. So when we are doing predictive work analytically, a number comes out from an equation, but we actually don't understand what it physically means. So
Right.
but when you start to do the testing, those numbers then actually mean something.
Exactly. Okay. Yeah, that makes a lot of sense. And also, I mean, just having a hands-on experience,
Sure.
that reinforces the learning as well. And like you said, it makes it mean something. So, yeah.
And also, Leanne, I mean, we have muscle memory. So, when we do things repetitively,
Yeah.
then certain things become part of our muscle memory. So we learn to do things through repetition. I mean, a lot of flying is muscle memory. So yes, the development of the cognitive abilities alongside your muscle memory is also part of that learning to judge.
Right, that makes sense. Now, you've worked on sophisticated flight simulators from hydraulic motion platforms to certified training devices. How do you think simulation is evolving, and where does it genuinely outperform traditional training?
Well, I mean, I don't think there is any substitute for real training. That has to happen. But there are lots of aspects which are important. So, for example, simulation is, from an aerospace engineering point of view, very, very important from a pilot training point of view, as well as from an engineering point of view. Now, especially when we come to do aircraft design. So when we do aircraft design, simulation is a fantastic tool. We basically produce digital twins, and when we produce these digital twins, we can learn the design trade-offs, the early engineering design trade-offs. Give you an example. Let's say I've been working on an aircraft, I've selected an engine, I have some performance criteria to meet. So if I wanted to play the what if scenario, what if my engine was to lose 10% of power due to some reason? What effect will it happen? What effect will it have on the aircraft? Whether it is on the rate of climb or whether rate of descent or whatever it is that I'm trying to measure. So a digital twin or a simulated environment allows us to play the what if scenarios in total safety. We are not committing hundreds of thousands of pounds in flight testing. We can actually do it in the comfort of our desk using a simulated environment. Now, I encourage all aspiring, budding aviation enthusiasts, aircraft designers to learn to create a digital twin. Once you have a digital twin, then it becomes easy to investigate technical changes, whether it is increasing this wing area or a control surface area, or how a control surface might act. We might start to look at flutter, etc. So basically, I am a great proponent of a software package, a public domain package called Explain. We use it from an engineering point of view. And I always say that if you can get your aeroplane flying in Explain,
Hmm.
then you can certainly get it to fly for real. So simulation to me does not replace the actual entity or actual aircraft, but it certainly allows you to sharpen your judgment. And I think engineering
Right.
is all about judgment.
Yeah. Well, and it saves a lot of cost too, I would think, and gives you that initial learning. And yeah, because if you're crashing with the simulator, then you're not losing a whole aircraft and saving the time and cost to rebuild as well.
I have a very interesting tale to tell you. When the NASA space shuttle was being built, thought of, etc., they needed to train the pilots. They didn't have the shuttle. So the pilots were trained on the shuttle, and when the first shuttle mission took off and when they landed safely, they asked the question, how did the shuttle fly? And the pilots responded, not as well as the simulator.
Right.
So they didn't change the simulation, they actually changed the shuttle. So the simulation technology is so advanced now that we can get very good realism, both from
Hmm.
a analytical mathematical point of view in terms of how things behave in reality. So it's very advanced, and these days, because of software enhancements and your visual technology, we can have very realistic flight simulations to supplement the real training. So as you rightly said, we can cut a lot of cost, training cost, by introducing simulation, whether it's from an engineering point of view or from a flying point of view.
Yeah. Okay. Now you've pointed out a growing gap. Aerospace curricula are packed with content, but hands-on facilities like wind tunnels are limited. What's the cost of that shift for industry readiness, and what can universities do about it?
Yes, I mean, again, it's something that I very strongly believe in, and I am a great advocate of hands-on training. It's like this. Universities are commercial entities these days, and being commercial entities is a growing, let's say, demand on them to be economically viable and to be, in some cases, if not profitable, certainly not loss bearers. So as a result, universities are always trying to reduce costs. Now, engineering, unfortunately, is a very cost-intensive area. For example, if you were to instruct somebody in mathematics, all you need is a blackboard and a chalk, and away you go. There's not a great deal of infrastructure cost. Whereas aerospace engineering, traditionally, you require mechanical elements, electronic elements, wind tunnels. So there is a lot of hardware required to impart that hands-on. And of course, space costs money these days. So, 1 square foot
Right.
somewhere, well, it's going to cost you money. So the universities are all the time reducing the cost by shrinking the footprint, the engineering footprint. Now, as a result, a lot of universities have lost their wind tunnels. A, they are expensive to maintain, and B, they take up a lot of space. Similarly, some of the more expensive experiments which require a lot of on costs, they have been removed from curriculums, or either they're being exposed to that experiment virtually, or they just talk about it, giving the students, I won't say a brilliant deal, but I would say something to think about. Now, I don't know whether you are sort of well versant with the Royal Aeronautical Society. We have a professional engineering institution called the Royal Aeronautical Society in the UK, and they look after the interest of the aerospace industry within the country and globally as well. So, for example, we have a RAES office in Washington as well. So the outgoing president, Dr. David Chin, had a presidential theme. All the presidents of the society will have a theme which they will promote throughout the year. And David promoted his theme, which was design, build, fly. He wanted the students to undertake the design, then building and the flying of an aircraft. Designing maybe doesn't take a lot of infrastructure, but building certainly requires a large infrastructure, and of course, flying also. We've got to get the students to appreciate the full cycle. We can't make large aeroplanes because the cost is going to be prohibitive, but certainly we can replicate the same ethos at a much smaller scale, like a UAV. It's a
Right.
small aeroplane. It gives the students a hand-on experience, but because the scale is small, it is economically manageable, and also it is manageable in terms of time. So when we look at the time management and financial management, a small scale UAV design, build, fly is certainly viable. Now, that requires a competent human resource to undertake this problem-based learning approach within curriculum. And I think that's where we lack. We don't have enough qualified teachers who would take this problem-based learning approach and basically take the students through a design, build, fly exercise in one academic year.
Hmm.
So it's not really the equipment as such, or let's say the infrastructure, which is hampering this design, build, fly cycle, is actually the institutional courage, is to basically do things differently and look at the same curriculum, but impart that curriculum slightly differently.
Interesting. Okay. Yeah, that makes sense. And so you're finding it's more of a individual teacher or limitations as far
Well, I
as the
mean,
teachers themselves?
I for my sins have introduced at my university this problem-based learning approach, where in one academic year, the students will actually design in
Hmm.
groups of eight, the teams of eight students each, and they will design a UAV per team against a prescribed criteria, and they will build it, and they will validate and verify the whole process, and then they will test fly it.
Yeah.
So yes, but it does take a lot of effort. So as I said, it's the educational courage to think of the curriculum slightly differently rather than the conventional lectures and exams.
Right. Yeah, that makes sense. So, is this something like a student should look into when they're considering what university they might go to as well? Like if they have
Yes, I think
programs
that's
that,
very important. That's very
uh,
important. The students should actually see what kind of practical exposure and experience is the university going to offer when they're there, because that also helps them become engineers. And I think that's the whole idea. You know, we want to be able to become engineers, not just a theorist who has
right,
no insight into the physical constraints that engineering poses upon us.
right, and practical experience as
That's right.
well. Yeah, that makes sense. Now, you've made a provocative point in the past that vertical lift is often energy inefficient, and nature offers clues, like one VTOL bird versus thousands of fixed wing birds. What should industry reconsider about EVTOL hype versus practical application?
Yes, I mean, this is a topic that I can talk endlessly, but I'm going to keep it brief. Electric, vertical takeoff and landing. Now, VTOL is not new. Vertical takeoff and landing, for example, 1934, there was a crackpot engineer whose name was Botziat, and he produced a quadcopter, a massive quadcopter, which is basically what we now call the distributed electric propulsion. And he particularly wasn't very successful because the power to weight ratio, his structure was very heavy, his motors weren't man enough, so he wasn't able to progress that idea any further. But then, of course, we've had helicopters. Helicopters came about, and the first commercial helicopter service was, I believe, in 1952 or 1953. So VTOL is not new, right? Now, all we've done is this EVTOL. We have taken away the internal combustion engine or the gas turbine engine and replaced it with an electric motor and a battery. The principle remains the same. Vertical takeoff and landing aircraft are energy inefficient because we have to, or we can call them powered lift. So you have to provide the lift that overcomes the weight of the object through thrust. Now, if you look at Mother Nature has tiny insects, and practically all insects can do vertical flight. Now, to them, air looks like goop, very, very thick, viscous stuff. So when they flap the wings, they can go anywhere they want. When we start to look at birds, we come to realize that there is only one true hoverer, and that's a hummingbird. Hummingbird has a ability to hover vertically. But not only that, it has a fantastic ability to articulate its neck in such a way that the beak will stay perfectly still, whereas the body will rotate to accommodate any fluctuations in the air current.
Hmm.
So it is concentrated in one aspect alone, and that is to draw the nectar out of the flower. A hummingbird would, let's say, consume at least its body weight in nectar. And that's where the energy inefficiency comes. Now, Mother Nature then also then tells you that there are birds that they can travel hundreds of miles without any need for replenishing energy,
Right.
right? So the fixed wing birds are more energy efficient. And
Yeah.
Mother Nature tells you that in more ways than one. We look at the flight of the condor, we look at eagles, we look at other birds, and they are efficient soarers, efficient gliders, efficient flyers. Now, when we come to the use of technology, particularly the EVTOL technology, we have to understand one thing. What is the need? Now, often I say in public that we as engineers have answered the question, can we? Yes, we can make eVTOL aircraft, but we often dodge the question, should we?
Should we? Yeah.
And who for?
Right.
So the point is that what are we designing this technology for? Now, give you a very stark statistic. And the statistic is that only 11.7% of the global population has ever set foot in an aeroplane.
Really?
That is correct.
That is surprising.
Now, another stunning bit of statistic is that 84% of all the global wealth is in the hands of 11% of the global population. So now
Wow.
you immediately see that 11.7% sitting in an airplane are the ones who actually have money. So flying isn't a poor man's sport, as they say, right? You have to have money to be able to fly because air tickets are expensive. Now, another thing that we have to start to think about is helicopters have been around since 1952 commercially.
Hmm.
How many people use helicopters as a mode of public transport? Very, very few,
Very few. Right.
right? Now, the second question that I often ask people is that if vertical flight was that interesting, well, helicopters have been around since the 50s, how many heliports have you got in New York City? As it turns out, only three.
Really? Hmm.
Yes. How many heliports have you got in London? Answer is two. So basically, we are saying that there really isn't a great deal of demand. So when these EVTOL people came out seeking venture capital to develop this technology, they were saying this is going to be the next big revolution in aerospace, and we are going to have urban air mobility. We're going to have these things flying over cities. Now, of course, that's not going to happen. Why? Because this technology is not going to scale nicely for mass commuting. And there is many reasons. For example, who's going to use an expensive mode of transport? I mean, already 11% fly, but of those 11%, less than 2% has ever been anywhere near a helicopter. So it's a very restrictive market. Not only that, the thing that I always argue with all these eVTOL pundits is we haven't got the infrastructure. Where are these vertiports? These
Right.
vertiports are going to cost a lot of money to build. So when you start adding the cost of the vertiport, the return on investment, that has to go on to each flight. How big are these vertiports going to be? Then what you realize that these aircraft are not going to be cheap, they're going to be expensive. So when you add a £5 million vertiport and add a £5 million or $5 million UAV or a eVTOL, it's a lot of money.
Yeah.
Right. So then we can't really say that the cost of flying in one of those is going to be like an Uber. So a lot of these companies you may have heard in the past saying that, the cost per mile would be very much like Uber Elevate or something like that. And of course, they are missing very elementary calculations such as the depreciation on the assets, the investments that they have made already to produce the product, et cetera, et cetera. So in terms of mass commuting, I don't think this technology will scale up. However, there are pretty damn good uses of this technology. For example, medical response, we can look
Hmm.
at logistics, we can look at safety critical and time critical applications, you know. So there's many applications for this EVTOL technology. But in my humble opinion, I don't think carrying people in a congested city environment as a mode of mass transportation, I think the argument is flawed.
All right. Well, Dr. Ali, thank you so much. I know this is a fascinating conversation. We could probably go on all day. In the interest of time, though, I have one more question for you. I appreciate your time. Thank you so much for joining me. Now, if you could install one operating principle into every engineer entering aerospace today, something that would make them more effective, resilient, and ethical, what would that be?
That's a difficult question. uh, right, let's think. Did I say at some stage that engineering, we are trying to inculcate the ability to judge, the judgment, the judgment's an important. So let's see if we can actually work that one through. So if I said engineering is a judgment in uncertainty, that when we are faced with an uncertain environment, and if you are then able to judge something or come to a conclusion, so then that will be an important aspect. Now, also at some stage, we talked about perfection, as to what is perfection. So I'm going to summarize this as follows. Perfection is direction. It is not the destination. Therefore, engineering is judgment in uncertainty.
That's interesting. Yeah. So judgment in uncertainty.
Yes.
Right.
So perfection is direction. So we are not going to chase perfection as a destination
Hmm.
because there is no such thing as perfection.
There's no such thing. I was just going to say that as well. There's no such
Okay, so
thing.
so perfection says that you have to do things right, you have to do things correctly. So perfection gives you the direction. So it is telling you to go towards something nice. Now, what is something nice? We don't know, right?
Hmm.
And another saying that comes to my mind is one man's ceiling is another man's floor. So basically, perfection is a bit like that. It's direction. It is not our destination. Our destination is judgment in uncertainty.
Yeah,
Being
I
able
like
to
that. Hmm.
operate in an uncertain, and that's what makes us different to machines.
Right. Well, and you have to be in that space to innovate because innovation requires that uncertainty, right? It's like you're getting past that uncertainty to figure something out. And so it's being okay with being in that space of
Absolutely,
uncertainty.
because it's
Yeah.
it's the fear. You mustn't have the fear of the unknown, because if you fear the unknown, then you will never be able to make progress. And that's basically what engineering is all about. Engineering is about making that correct judgment in an
Hmm.
uncertain environment and eventually come out triumphant.
Awesome. Yeah. Well, Dr. Ali, thank you for sharing your perspective and for your
My
the work
pleasure.
that you're doing. It's yeah, fascinating. You're not just developing aerospace capability, but human capability. You're really investing in
Absolutely. That
that.
is very crucial.
Yeah, future generation. Now I mean, teachers are invaluable, especially those who have a lot of practical experience and who are, really advocates for the students and advocates for increasing knowledge, the knowledge base. So for listeners who want to learn more, to follow your research or connect with you, where's the best place to find
But
you?
LinkedIn would be the best. So if you type in Dr. Rashid Ali, I'm sure you will find me through LinkedIn. I do regularly post the achievement of my students. What a wonderful way to celebrate their successes. I do that very regularly, and I do keep in touch with my old students through LinkedIn as well. And I always tell them that a student isn't just for 3 years. When I have a student is for life.
Yeah.
So I am your mentor for life.
Oh, yeah, I love that. And yeah, it gives them that opportunity or welcomes them to reach out to you. And I'm sure when students do, it gives you more insight as well. So, yeah,
Absolutely.
yeah.
Absolutely. That is correct.
And yeah, so everyone, if you're interested, please reach out to Dr. Ali. And for those of you who are listening, if you enjoyed the episode, please subscribe, leave a review, and share it with someone who cares about the future of aviation, autonomy, and developing the next generation of engineers. So please tune in to the next episode of Industry Ignited. Until then, stay bold, stay curious, and keep igniting industry.